In this video, I want to talk about SR-Latch or set reset latch. So you remember from the previous video that we were able to use two inverters to create a bistable circuit. That even though it had the memory capability to store 1 bit of information, it was not that useful because we didn't have any input to control what is the value that is being stored in the bistable circuit. So for the SR-Latch, we modified the design of the inverter and we come up with this design. So instead of having two inverters, now we have two NOR gates, N1 and N2 here. And then since for these two NOR gates we have two inputs each, we use from each we use one of the inputs and we connect it to the output of the other NOR gate, but the two remaining inputs are being connected to R and S signals that we can specify. So before I move forward, let's just quickly go over the truth table of a simple two input NOR gate and see what we have. So let's say we have this simple NOR gate. We have input A, we have input B, and we have output Y. So if I want to create the truth table, you remember we wrote the inputs to the left and the output to the right. We went over all the possible combinations of the two inputs. So since we only have two inputs, there are 4 possible combinations from 0, 0 to 1, 1. And then now for each one of them we can find what is the value for Y, which is the NOR of A and B. So when both of them are 0, OR of A and B is 0, which makes it complement to be 1, so Y is 1. When A is 0, B is 1, OR of A and B is 1, which makes it complement 0. When A is 1, B is 0, the same thing happens. So the output is 0. And finally, for both A and B being 1, we have A or B being 1, which makes it complement to be 0. So we have 0 here. So this is the truth table of a two input NOR gate. So one thing that I want you to pay close attention to are these two lines. As you can see here, when only one of these inputs is 1, the value for other one does not matter. So as you can see here, A is 0 but B is 1, right? So the output is going to be 1 anyways. So if we have, let's say, A to be X, the output of the NOR gate will be always 0. The same is true for the second row too. When A is 1, it doesn't matter whether B is 0 or 1. The output is going to be 0. So each one of these rows with the final row, basically you can think of it as the second row and the last one as B being 0 and A being X, or don't care. Or for the third row and the fourth row equals A being 1 and B as don't care, because we have both possible values for B, right? So this is something that I want you to pay attention to. So now that we have this thing covered, let's just see how we can analyze this SR-Latch. So since we have both R and S as the inputs and we have Q and Q bar as the outputs, that means that we can create a truth table too. On the left side we have the two inputs S and R. On the right side we have Q and Q bar as the outputs. So since we have only two inputs, that means we have 4 possible combinations. So if I want to write the 4 possible combinations, we have R and S, Q and Q bar. we have 0, 0, 0, 1, 1, 0, and 1, 1. And then we want to know what is the value for Q and Q bar for each one of these rows. So the way I go through these different combinations is that I first go through the second one and third one. Then I will go through the first one, and then I will go through the fourth one, right? Because the second one and the third one are practically the easiest ones that you can do, right? And then based on that, you can understand what happens in the third one and finally in the fourth one. So let's just go through these possible combinations. So in the first combination, we have S to be 1 and R to be 0. So R here, which is one of the inputs to this NOR gate, and 1 is 0. S, which is one of the inputs to this NOR gate, and 2 is 1. So now based on these values for R and S, what is the value for Q and Q bar? So for this one, as you can see, we have R to be 0 and we have the other input to be Q bar. So Q is basically R NOR Q bar, right? So when R is 0, what is the value for Q? So if Q is 0, or if Q bar is 0, that makes 0 or 0, and then the complement Q becomes 1. On the other hand, if Q bar is 1, then we have 0 or 1, which is 1, its complement becomes 0. So as you can see, we can have both of these values depending on the value of Q bar. But what about this one? So for this one, we have Q bar to be S or Q and then bar. And then let's say we have S to be 1. So when S is 1, we have 1 or Q, which is going to be 1 itself. If you remember, 1 was the null element of the OR operator. So because of that, the value for Q does not matter for us in order to calculate what is the output of N2. So since that is the case, we start from the output of N2. Because the output of N1, depending on the value of Q bar, can be either 0 or 1. But the output of N2, since one of its inputs is 1, it's going to be always 1. Sorry, it's going to be always 0. Because we have 1 or a value which is 1, its complement becomes 0. So let me just repeat. For N1, since we have one of the inputs to be 0, the output basically depends on the other input. So here, Q bar. For N2, since we have one of its inputs to be 1, its output is always 0. So it doesn't depend on the value of the other input. So now that we have this, we can say Q bar is 0 now. So when Q bar is 0, this signal is being passed to the other input of N1. So now we have 0 NOR 0, which makes the output to be 1. So when Q is 1, let's just see if N2 stays at its previous value. So when Q is 1, that means that this value 1 is going to be transferred to this input. Now we have 1 NOR 1, which results in a value as 0. So that means that we started from S. We calculated the value for Q bar. Based on that, we calculated the value for Q. And then we double checked if that value for Q changes anything in the value for Q bar, and we concluded that it doesn't change that value. So the conclusion here is that when R is 0 and S is 1, Q becomes 1, Q bar becomes 0. So since we usually work with Q, and this combination, this configuration of R and S makes Q to be 1, we just say that this configuration sets the output of the SR-Latch. So this is the first combination that we wanted to go over. Let's just go over the second one. In this configuration, we have S to be 0 and R to be 1. Now, let's just do the same analysis. Between these two NOR gates, which one of them we know the output for sure? For N2, Q bar is S NOR Q. So when S is 0, depending on the value for Q, we have either 0 or 1 for value of Q bar. But for N1, Q equals R NOR Q bar. So when R is 1, no matter what is the value for Q bar, the output for Q is going to be always 0. So based on this, since R is 1 and S is 0, the value for Q is going to be 0. So this is passed through this wire as the other input of N2. So now we have 0 NOR 0, which based on the truth table that we had in the previous slide, makes the output to be 1. So now let's just check and make sure that this value being 1 doesn't change the value for N1. So we have 1 being delivered as the other input. So we have 1 NOR 1, which in fact is going to be 0. So for the second case, we have started from R, we calculated Q. We said that now that we have Q, we can calculate the output of N2, which is 1. And then this input is going to be delivered to the other input of N1. So now we have 1 NOR 1, which is again 0, right? So that means that whenever this combination happens, R being 1, S being 0, the output or the Q is going to be 0. So because this is the case, this is usually referred to as reset. So set is when Q becomes 1, reset is when Q becomes 0. So as you can see, using these two inputs and in this configuration, we have control over what is the value for the output. This is something that we didn't have before for the bistable circuit. Since we didn't have any inputs, we were not able to control what is being put at the output. But still, we didn't talk about the memory functionality. So let's just go over the next combination. So the next combination is for when S and R are both 0. So in this case, we have R to be 0, S to be 0. So if I write the function for N1, we have Q to be R NOR Q bar. And for this one, we have Q bar to be S NOR Q. So now, in these two NOR gates, we have one of their inputs to be 0, both for N1 and N2. So now, using the truth table from before, can we say anything about the output of any of these two NOR gates with certainty? Because we said that if one of the inputs, either S or R, is 1, the output for that NOR gate is going to be 0. That was actually the case for the previous two combinations. But for this one, we cannot say anything. So since we cannot say anything directly from the inputs, what we can do is that we can just do whatever we did for the analysis of the bistable circuit. Since we are working with binary values, the value for Q is either 0 or 1. It cannot be anything in between. So let's just, for the first condition, we assume that the value for Q is 0. Or more specifically, the previous value of the Q is 0. A fraction of a second before we change the inputs, its value was 0. So now let's just see what happens when we assume Q is 0, or when the SR-Latch is in reset state. So when Q is 0, this signal is going to be delivered to this input. So we have 0, 0 as the two inputs of this NOR gate. So 0 NOR 0 is going to be 1. Now we have this 1 to be delivered as the input to this, the first NOR gate, and 1. So 0 NOR 1 equals 0. So as you can see, we start with the assumption of Q being 0. Based on that, we calculated Q bar going through this N2. And then based on the calculation for Q bar, we went back to N1 and we verified that when Q is 0 previously, it remains at 0. So that was the first condition, or the first possibility. Let's just see what happens for the second one. When both R and S are still 0, but we have Q to be 1. So in this case, again, we cannot say anything about the output of these two just by knowing S and R to be 0. But since we assume Q is 1, we can say this value is going to be delivered to this input for the N2 gate. So now we have 1 and 0 as the two inputs of this NOR gate. So 1 NOR 0, it's going to be 0. So this 0 now is being delivered as the second output, the second input of the first NOR gate, and 1. So we have now 0 NOR 0, which is going to be 1. So as you can see, when R and S are both zeros and the previous value for Q was 1, following the path of signal, the output or the value for Q remains as 1. So that is what we call as the memory functionality for the SR-Latch. So we have the case for which S is 1, R is 0, which makes Q to be 1. So that is the first case, or that is the set case. Then we have S to be 0, R to be 1, which makes Q to be 0. So that is the reset case. And then if we have both R and S to be 0, the output for Q remains at its previous value. So if it was 0, it remains as 0. If it was 1, remains as 1. So that is the memory functionality. So there is one other case left, and that is when both S and R are 1s. So when both S and R are 1s, then we can know the output of these two NOR gates with certainty, right? We don't have to do any extra analysis. One NOR whatever is going to be 0. One NOR whatever is going to be again 0. So when both R and S are 0, when both R and S are 1s, the outputs for Q and Q bar become 0. And you can follow the path of the signal both for this one and this one to verify that this state remains. As long as S and R are both 1s, the outputs are going to be 0 for both Q and Q bar. So let me just quickly summarize what we had so far. So we have S, R, we have Q, Q bar. When both of them are 0, Q is the previous Q, Q bar is the previous Q bar. You see the same analysis that we did here for Q, we can do it for Q bar too. So that's why when both S and R are 0, Q is the previous Q and Q bar is the previous Q bar. The second case is when S is 0, R is 1. As we said before, this is the reset case, which makes Q 0 and Q bar 1. Then we have the 1, 0 for S and R, which makes Q to be set or 1 and Q bar to be 0. And finally we have 1, 1, which makes both Q and Q bar to be 0. So as you can see, we have the capability to set and reset the SR-Latch. So that is equivalent to being able to store a bit of information in this latch. So if you want to store a value for 1, a value of 1, you just put S to be 1, R to be 0. If you want to store a value of 0 in Q, you put S to be 0, R to be 1. You have the functionality of memory too. So if you make S and R to be both 0, whatever value it was stored in the SR-Latch before, it remains at its previous value. But we have this kind of weird combination as well, which when we make S and R both 1s, both Q and Q bar become 0. So even though we started from the bistable circuit, and for the bistable circuit we had basically 2 inverters connected back to back, and in that circuit we had Q and Q bar to be the complement of each other, right? For the SR-Latch, that is not necessarily the case, because we have now a different design. We have both S and R as the inputs too. So for when S and R are both 1s, then we end up in this unwanted situation for which Q and Q bar are both 0s. So they are not complement of each other. So as I said, when both of them are 0, we have the memory functionality, and then when S and R are both 1s, then we have this invalid state in which Q bar is not the inverse or the complement of Q. So let's just recap what I talked about the SR-Latch. So SR again stands for set reset latch, and it is used to store 1 bit of state or value for Q. So we have control over the value that we want to store in the SR-Latch, and the way that we do it is by choosing the values for S and R. So if we want to store a value of 1, we put S to be 1 and we put R to be 0. That makes the value for Q to be 1. If we want to make the output 0, or in another word, if we want to store a value for value of 0 at Q, we have to make S 0 or 1, which result in Q being 0. And for the memory functionality, when S equals 0, R equals 0, then we have Q to be the previous Q. So these are the functionality for the SR-Latch, and you see the symbol that is commonly used for the SR-Latch in digital circuit is like this. We have R and S as the two inputs, and we have Q and Q bar as the two outputs. However, SR-Latch suffers from a big problem, and that problem appears when S and R are both ones. Because of that, we have both Q and Q bar to be 0, and Q is not the complement of Q bar anymore. There is another drawback in using SR-Latch, which may be not that obvious. But why do we need two inputs, S and R, to be able to set and reset one single output? So shouldn't be only one variable or one input enough? Because we are not storing values other than 0 or 1, right? So if you only have one input, which either can be 0 or 1, and based on that value, the output is 0 or 1, that's a much better design. So because of these two main reasons, we will move from the SR-Latch, and we do modifications to create what is called as D-Latch. I will go over the D-Latch in the next video.